All right, so last time, and let me go ahead and I'll pop this open because this is where we're ultimately going with this. We're going to be looking at an algorithm called ShuntingYard. So there's a couple of rationales behind this. On one hand, this is kind of showing us the existence of an algorithm to help us deal with order of operation. If you were writing code that required you to take advantage of orders of operation, you know, kind of like something like this, that where you had to take into consideration parentheses, or that multiplication happens before addition and subtraction, and that kind of stuff. So that's kind of the algorithm side of this. The data structure side of this, if we just kind of look at our picture here, is we have our effectively an input queue, an input linked list, and this is effectively what we created today for our homework assignment today, is this piece. And things from there go either to an output queue or an operator stack. So we've already done linked lists, we've already done stacks, and now we're just kind of throwing our final linear linked list into our linear linked data structure into this, and looking at a queue, where a queue is a first in, first out queue, as opposed to a stack being a last in, first out queue. So we can think of a queue as like a line. You get in line first, you're the first one who's going to get served. First come, first served. Okay, so we're going to be using those couple of tools to be able to accomplish what we're trying to do here. So we're going to go ahead and we're going to rewrite our linked list, especially since we're actually writing the easier version of our linked list here. We're not going to have to do the add and remove from the middle. We're basically adding things to the front, adding things to the end, removing things from the front. That's the, and also, let's see, yeah, I think that's correct. And that'll allow us to have the ability to handle a queue and a stack. Okay, and then we'll have this tool to do that. So the homework assignment for today was to take a string that looks something like this, or like in our example, I think I said, you know, let's say you took something that looks like this, and it says participants can now see my screen. Did you just now see my screen, or have you been seeing me all along? I just got a pop-up saying participants can now see my screen. Have you seen everything I've been doing up to this point?
Yeah, we saw it.
Okay, I don't know, maybe it was just a weird Zoom thing. Okay, so in any case, you know, for today we were taking in a string that looked like this, and you can hard code the string. You'd have to read in from the user or anything. And then we're ultimately turning it into a linked list that looks like this. And what we're accomplishing there is this piece of ShuntingYard, giving us our source input so that we can operate off of that. All right, so let's go ahead and start looking at that and remind ourselves how strings work. Let's see here. I am going to to create a new, click there, okay, yeah. I'm going to create a new project. And we'll go ahead and save this. We'll call this ShuntingYard CSC300 fall 1. Okay, so that'll give us kind of our starting point there. And just before we start doing our linked list portion of this, let's remind ourselves how our C style strings actually function. Make sure I have to let everybody into the room. Yeah, looks like we're good. All right. So we're going to include, I think it's just string like that, using namespace standard. So So we're going to create a string S, a lowercase string, whatever. And I'm going to operate. Oh, there it is. And I'll grab this string as our example. That gave us some very weird double quotes. There's that. And I'm going to use IOStream. Let me just make sure I'm bringing our string library in here correctly or get that fixed up. Yeah, it looks like it. So I'm creating a string name S. I'm setting it equal to this guy. And then we are operating through that. Let's see, length of string. Is it string? Do we have to use string length for that, or does string have a C++ string length? I know I spelled it wrong. Just a length function. Yep, string.length. Okay. All right, so we're printing out S. There's s.length, so very much Java style. And then we're going to go ahead and just do a quick for loop. We're going to I is equal to 0. I is less than s.length. I plus plus. And we'll go ahead and do cout s at bucket I and L. And that should show us all the individual characters in S. All right, so here's our string. Here's the number of total characters. And there's the individual characters. So this kind of gives us enough information to operate off of. Let's make sure we remind ourselves concatenation. We'll just say S2 starts off as the empty string. We'll say S2 is equal to whatever S2 currently is, concatenated with S at bucket I. And then we'll go ahead and print out S2. So that should show us our concatenation stuff. And there is our example of concatenation. All right, so that should introduce us to the tools we're going to be using enough here to effectively do this homework assignment. All right, so any questions about any of this stuff? I know we had done this before, but this is a good refresher. And well, I needed the refresher since I bounce between languages all the time. But in any case, no big deal. Looks very much like Java. And, you know, a couple little caveats here. Instead of, you know, like s.char@, we can get it using array syntax. There might even be another function that lets us get something, but you know, we're seeing how this works. So any questions about this before we start implementing our linked list of strings? Okay, so let's go ahead and start building our linked list. So I'm going to create a new file and we're going to call this guy linked list. I'm going to call it linked list of strings. Just so we can be explicit here what we're working with. All right. Actually, I don't know what I was trying to accomplish there, but we need our header file. So we'll make this the HPP. So we'll go ahead and we're going to need to include a string. And I don't think I need namespace standard for the string class, but I do need it for cout. So we'll see if it screams at us when we do this, because I don't want to just willy-nilly put the namespace all over the place. So this is our, let me just steal this guy real quick, just because I'm a suspicious speller. All right, so we have our class like this. We have our private section for our linked list of strings we're going to keep track of. Now we got to think about what we need to do to accomplish our ShuntingYard algorithm. You didn't have to do all of this for the assignment. You just had to get the stuff into a linked list. But since we're going to be implementing both a stack and a queue, it's probably going to be handy for us to keep track of the beginning and the end of our list using tail, head and tail. So we're going to be creating a node class. So let's go ahead and create our node class while we're here. So we'll say node HPP. And actually, we won't need string in the other one because we'll be having a collection of nodes. We're just going to let's actually rename this. I'm going to call this guy string node. Kind of with the idea that now what you could do is you could create a linked list that that is a linked list of nodes, and maybe nodes is a generic abstract class, and then you have string nodes and int nodes and things like that. So in the end, we could create kind of a single, more kind of universal linked list if we wanted to. We're not going to in this case, but just kind of wanted to push us down that line where you could. You can say, I'm going to have a linked list of a generic node. And then instead of actually implementing node, we just use node as the base class for string nodes and int nodes and char nodes and person nodes if we wanted a linked list of person objects or something like that. So that would allow us to write linked list a single time. But we're not going to do that in this case, but I'm just naming it kind of purposefully. All right, so in here, we're definitely going to need the string class. And we're going to have our class string node. All right, and a node is going to know about its payload. It's going to know about its next node. And because we're going to be keeping track of tail, let's make sure it knows about its previous node. All right, so we'll have a string payload, a node pointer, next node, and a node pointer, previous node. And this is in the private section. The public section, we're going to have our constructor here, and we can have our constructor take in our payload. And I'm going to go ahead and give ourselves our getters and setters because we know we're going to need to get the payload. We know we're going to need to be able to get the next node, get the previous node, set the next node, set the previous node. So this guy's going to return a string, get payload. This guy's going to return a node pointer, get next node, node pointer, get prev node, nothing, set next node to a node pointer n, void set prev node to a node pointer n. All right, so those are the functions that we're going to implement inside of our node class. We grab all these guys and let's go ahead and implement string node HPP. New file, string node.cpp. This guy will include string node HPP. And then we're going to be implementing all these dudes. Go ahead and put this piece in all of them. All right. So here's our constructor for a string node. So we'll set this payload is equal to the payload that was passed in. And then we'll also set this next node equal to null. This prev node equal to null. So when we first build a node, it has a payload and it points nowhere. Get payload will return this payload. Get next node will return this next node. Get previous node will return this prev node. Set next node will set this next node equal to whatever was passed in. Set previous node will set this prev node equal to whatever was passed in. All right, so there's our starting point for our nodes. And I know I'm kind of doing that pretty quickly, and hopefully I didn't introduce too many bugs in there, but you know, this is all pretty much repeat stuff. We've done this a bunch of times, so this is more just tedious crap than any new material or anything. Okay, so that should give us at least our first pass at our string node there. We'll come back and clean up any mistakes that I obviously did on purpose once we get to that. Oh, and by the way, just I do apologize for last minute moving class to Zoom. I had forgotten my wife needs me here at home to meet with a service person who's coming at noon. So I was going to have to rush out of class anyways. I should have done this last class, but yeah, it's nothing serious. Just I need to be here at home at noon is the punchline. Okay, so going back here, linked list of strings. I'm actually going to remove the include string here for a second, because I don't think we're going to need that in here, because this guy just needs to know about nodes. So we're going to include our string node.hpp in here, because this is going to be a linked list of those dudes. All right, so we're going to keep track of a string node pointer called head, a string node pointer called tail. Let's go ahead and keep track of our count. That's kind of been a new tradition where we decided, you know what, it's not a horrible idea to remember the number of elements that are in our collections. Okay, so we'll have our head, we'll have our tail, we'll have our count. Public functions, we need to be able to add to the front. Let's see. Yeah, we need to be able to add to the front because we have a stack involved. We're just kind of thinking about what are the functionalities we want to have in here. This guy is a traditional linked list, but it's going to effectively operate as a queue. When we build it, we'll be adding to the end. We'll remove from it. We'll be removing from the front. So this is an input queue. This is an output queue. And then this is a operator stack. And we'll see how that stuff works when we actually talk about the algorithm here. For right now, we just know that these are the three animals that need to exist. And from our perspective, these are all the same kind of animal. They are a linear linked data structure of strings. So we just need to make sure that it's capable of these various things. It needs to be able to operate as a first in, first out thingy. It needs to be able to operate as a last in, first out thingy. And we don't need any of the fancy stuff in between of adding or removing in the middle where we're performing the heavier surgery and stuff. So it's not a difficult, super difficult implementation. We just want to kind of create a single animal that lets us pull off the various things we're going to be trying to accomplish here. All right, so that means we want to be able to add to the front. Okay, so we'll call this guy add front and it'll take in a payload. We want to be able to add end and it'll take in a payload. We want to be able to remove, I'm sorry, that's not void. Because of the way ShuntingYard is going to work, I'm going to go ahead and just do something a little bit ahead of time. Previously, when we like removed from the front, we actually had it return the payload. I'm going to go ahead and have it return the string node because we will be relocating. You know what? It's actually not going to matter. I'm not going to do that. We're going to keep it the way we were doing it before. So when I remove from the front, I'll extract the payload and we'll just throw away the string node and we'll build a new one when we go and put it on the other guy. So that means we're going to have a string get returned here, which then means we now need to include the string guy here because he's not coming out as a string node. He's coming out as a string. So we're going to return a string. We'll call this guy remove front. We have another string, remove end, void add front. Bring payload. I want to just check something here. I have a recollection that I wrote int in several places in here. Nope. Those took in notes. So add front will be adding a string. Add end. We'll be adding a string. We can do the push and pop stuff if we want. Push will add to the front. Pop will remove from the front. We can put those in there if we want, or we can just make sure we call the right functions. Doesn't really matter as long as we know effectively what we're pulling off here, because we're really creating kind of a hybrid data structure. A single, we're calling it a linked list of strings. It's a single linked list of strings that can behave as a queue, that can behave as a stack. So it's kind of a multi-purpose tool instead of creating a single queue and a single stack, because they're really the same kind of animal at the end of the day. All right, so add front, add end, and then let's go ahead and give ourselves a count, and then give ourselves a display just so we can make sure that things got put in there the right way. That looks pretty decent. All right, so we want to go, oh, I need my constructor as well. All right. Constructor will take in no parameters. Okay. So copy all those. Let's go implement them. So this is going to go inside of linked list of strings.cpp. Linked list of strings CPP. And we're going to go ahead and include linked list of strings.hpp. We're going to implement all these dudes. Put these pieces in here. So now let's implement these guys. So our constructor for this is going to set this count equal to 0. It's going to set this head equal to null. It's going to set this tail equal to null. So that's what a fresh linked list of strings is, where we have no head, we have no tail, and count 0. All right. Add to the front. Okay, means that we're going to make head point to this guy. But so we ask a couple of questions. We'll say if this head is equal to null. So if we have the empty list, we could have also asked if count is equal to 0. So if head is equal to null, now any way you cut it, we're going to need to be creating a string node. Oh, I did make a mistake here with our int payload, which is kind of funny since I did it, I think, after the fact. These guys are all string payloads. Oh, I did it correctly down here, just not for add front, add end. That's a string payload, and this guy's a string payload. All right, so if so we need to create our string node. I'll make sure we've imported string node here, linked list of strings. HPP has our string node brought in, so we're good there. So we'll say string node pointer n is equal to new string node, passing in our payload. All right, so now we have a fresh node that we want to put onto our list. If the list is currently empty, then that means we want head and tail to point to this guy. So this head is equal to n. This tail is equal to n. And any way you cut it after this function, this count will be 1 bigger than it used to be. All right, so this is only if we're dealing with the empty list. If we're not dealing with the empty list, then presumably head already points to something and tail points to the correct place, whether it's the same thing head points to in the one list or it points to the correct tail someplace else. Doesn't really matter. In any case, we need to update what head points to. So we're going to say we need n to point to the same place as head points to. So n set next node to head. So now n and head both point to the same place. And this dot head is equal to n. So make sure n points to the same place as head, and then we can update head to point to the new front. All right, and we don't need to update n's previous node because it's at the front of the list. So the default previous node is null, which is correct. Okay, so this is what we do regardless of, well, this is what we do for adding to the front. Adding to the end is going to be pretty similar, dealing with a tail. Actually, I'll steal most of this actually. So we'll create our new node. We can ask ourselves if head is null, or we can ask ourselves is tail null, or we can ask ourselves is count equal to 0. So really what we can do here is we can say if head is null, we could actually just go ahead and call add front. No harm, no foul. I'm going to go ahead and just leave it in here because I'll have to ask this question ahead of time. Actually, you know what? It's not that big a deal. I'll just do that. I'll say this add front of payload. But then what I'll need to do is I'll put that inside the else. Okay, so if this is the empty list, go ahead and just call add front. We already wrote it. Okay, but remember add front takes in a string, not a string node. So I'm only going to actually build my string node in here if I'm in charge of adding it. If we're offloading the work to some other dude, in this case, our add front, we'll just pass him the payload and let him build it. Okay, otherwise we'll go ahead and build our node. And now this is where we need to update tail. All right, so we want n to be the new end of the list, which means that n's next node is already set correctly. It's already pointing to nothingness because he's the new end. So we need to set n's previous node to be the same thing as tail currently points to. All right, so n's previous node will point to the guy tail currently points to. And then we'll say this tail is equal to n. Update that pointer. And then we want to make sure we move our counter into here. Otherwise, we would be double counting because add front will increase the count. And if I had the count plus plus outside of this guy would increase the count as well. So a couple little catches here that we just need to be a little bit careful of so our count doesn't get off. All right, so add to the end gives us this guy. Create our new node, set his previous node to be the same thing as tail currently points to, update tail to point to this guy who's now the new end of our list, and then increment our count. All right, remove front. In this case, we're actually removing something from the list. So we need to get the node to remove. So this is going to be string node pointer. Actually, we don't need it as a string node pointer. We just give this as the, you know what, I want it as a string node pointer. So let's say string node pointer temp. Since we're removing from the front, this guy is going to be equal to whatever head is currently equal to. Then we'll make. Now, in this particular case, we could do error checking and ask the question like, hey, don't try to call remove front if we have nothing, you know, in here. So we could conditionally say if this head is not equal to null. If there's something in this list to return, let's go and do some stuff. So we'll go ahead and link to the dude that we're ultimately going to return, whose payload will ultimately return. Then we'll update head to be equal to temp get next node. All right, so initially we store the current front of the list inside of temp. Then we update head to point to that dude's next node, who's going to be the new head of the list. Then we'll say head set prev node. Actually, we need to ask kind of a question here. We're going to say if this dot head not equal to null now, then we can say this head set prev node to null, because this is now the new beginning of the list. Keeping in mind here that we only can do this if head is pointing to a real thing. It's possible if this was the one list that when we just updated head, we actually pointed now to nothingness. All right, so only if head currently points to a real node do we want to go ahead and update that node's previous node to be null, because it's the new head of the list. There isn't something before him. Then we want to set temps set next node to null, fully disconnect that. ultimately we want to return temp. I'm going to say string val to return is equal to temp get payload. So we'll preserve the value we're going to return. Then we'll go ahead and delete temp. And we'll return val to return. The very last thing is we'll say this count minus minus. So if there's something to remove from the front, go ahead and remember the dude we're going to be removing so that we can delete him. Go ahead and update head to be the next guy. If the next guy is a real guy, update his previous node to nothingness because that's the new head. Fully disconnect temp by setting his next node to null. Remember the payload that we're going to be returning because we need to delete the memory associated with temp. So we're going to delete the node after we remember the string we're going to return. Decrement our count because our list is one smaller than it used to be. Actually return the string. Okay, so that's remove front. Why do I have multiple add friends and add ends? Add front, add end. Oh, I got overzealous. It looks like I really wanted to have those functions. So we don't need to write those twice. So we can get rid of that there. All right. So that's remove front. Now let's write remove end. So we're only going to do something if this dot head is not equal to null. All right. So this dot head is not equal to null. You can ask the same question multiple ways. You can say, is tail not equal to null? Is head not equal to null? Is count not equal to 0? We're basically asking the question, does this list have something in it? Because you can only remove the end from a list that has something in it. All right, so if there is something in it, we'll go ahead and remember the guy that we're going to be removing, which is what tail points at. We're going to be removing the guy at the end. Okay. So then we want to go ahead and update tail to be equal to temp get prev node. So we want tail to point to the old version of tail's previous node. Then if this tail is not equal to null, let's check something real quick. Yeah, I had a recollection that I had put double equal sign here instead of not equal. It's correct up there. So if tail currently points to something other than null, that means we had more than one element in this list, in which case we want to set tails set next node equal to null because that's the new end of the list. That's the new end of the list. Hold on, let me. Oh, my wife's coming to get it. I just need to be here to deal with the guy after he's done. Okay, so we'll set, so if tail currently points to something real, we'll set tail's next node. Sorry, I just had to tell him that I would be out in 10 minutes. All right, so we'll, so if tail currently points to something real after we've updated it, if it points to something real after we've updated it, then we'll go ahead and update his next node to null, because now he's the new tail, it doesn't point anywhere. But that's only if he's a thing. Now, if we had the one list, he wouldn't even be a thing. All right, then we'll go ahead and we want to, just like we did up here, we want to set temps, set prev node to null, fully disconnect temp. And then we're going to say string val to return is temp get payload. That's the ultimately the string we're going to return from here. So we fully disconnect temp. Remember the string we're going to return. We'll go ahead and delete temp like that. And we did just remove something. Oh, what am I doing? We did just remove something, so I need to decrement our count. And then we'll go ahead and return val to return. All right, so remove end. We ask the question, is there something in the list? If yes, let's remember the last guy because that's the dude we're going to remove. Let's update tail to be the guy right before him. If that was a real guy, set that guy's next node to null because he's the new end. Regardless, fully disconnect temp by setting his previous node to null, which might be setting null to null. So we might be doing something that's a waste of time here, but it won't be illegal. Then remember the string we're going to return. Then go ahead and delete the memory for temp. That's the clean up our own mess thing. Decrement our count, return the string. So that's remove end. Get count is return this got counts. Then display, we want to go ahead and go through our entire list. I'm going to go ahead and teach a node how to display itself real quickly. So node will have a display. I already have IO stream here. I don't. So I will include IO stream using namespace standard. So in display here, we'll do cout this payload. Maybe followed by something like that. All right. So when a node displays itself, we'll just say payload followed by an arrow. We won't kick it down the line. This is just for visuals. All right. So then back in our implementation here for linked list for display, we're going to create a string node, cur node, and start this guy off at head. While cur node is not equal to null. So while it's equal to a real thing, we want to go ahead and say cur node display, and then cur node is equal to cur node get next node. As soon as we dump out of this, that means cur node currently is equal to null. And I'm going to go ahead and give myself IO stream in here. namespace standard. We'll do a cout. We'll say null is what it finally points to, and then we'll do an endl to kick it down the line. Okay. So now back here in main. We want to include our linked list of strings. We'll go ahead and create our linked list of strings, and let's just add some stuff to it. Add front string 1. And let's display it. See how much we broke. String node HPP, did we not include? String node HPP. Oh, it must be in using namespace. So that string class must exist inside of namespace standard. And it's not called a node, they're called string nodes. That's inside of string node. Same here, the same here. That's what I get for calling them different names. String node, string node, string node, string node. So next node inside of string node. So that's inside of this one, line 60. Is that the where we had the if statement it didn't return? Yeah, because this is a newer version of C++. Just like Java, it wants to make sure we return something. So we'll just go ahead and return the empty string in this case. We'll do the same thing here. Our feeling is that we're going to use this correctly, and that'll never happen. We won't try to remove end from a nothingness. So there's a working list. Let's just make sure add end works. So this should have the 2 at the end. Okay, add end seems to have a problem. So we'll say fix problem here first. All right, so we'll pick up there on Friday. We'll finish fixing this little thing. Then we'll write the algorithm to take our string and split it into pieces. And then we'll start walking through ShuntingYard, and we'll have our implementation of ShuntingYard due over the weekend. So if you wanted to look ahead and look at ShuntingYard and get an early start, you can, but we'll be talking about it in detail in class on Friday. So no homework due on Friday. Questions, comments, concerns, bribes? Okie dokie. I will see everybody on Friday.